right? Just going through the code. It's going to go through the for loop and look for value if it's equal to it and returns 1. And this gives you an example of some of the values that you get. Okay, binary search is a more sophisticated search. It's actually a much better search. What it does, and a binary search assumes an ordered array, an ordered list. It has to assume an ordered list. So it's got to be in order. So what the binary search does is it says, well, if the list is ordered, and I look at the middle value in the list, and the value I'm looking for is larger than the middle value, then I know that the first half of the list, the value cannot possibly be found in it. So I can discard that, take the second half of the list, cut it in half again, and do the same thing. This way it's a lot faster, because it essentially eliminates half the list every time. Instead of eliminating one by one, it actually cuts the list in half every time. This would only work with an ordered list. It's kind of like the index in the back of a book. If you're looking for something that begins with, or in a phone book or something, if you're looking for someone whose name is Smith, do you start on the A's? Of course not. You know the index is ordered, so you get straight to the S's and then the SM and so forth. And a binary search works that way too. It assumes an ordered list. The basic logic, there's a couple of different cases. It goes to the middle of the list, and it says, well, if the key is less than the middle element, then you only need to search the key in the first half of the array, so you can discard the second half. If the key is equal to the middle, that means you found it. We're done. The last possibility is that the key is greater than the middle element, and then you only need to search the second half of the array, so you can discard the first half. So the way it looks is, let's say this is your list, 1 through 9, and you're looking for 8. So the first thing it does is it looks at 4, and it says, okay, well, the value cannot possibly be found at 4, so now my list becomes this portion, the right 4, 6, 7, and 8. So 1, 2, 3, and 4 all get discarded automatically. Then I go and I cut into the middle again, and it's 7, which is still less. Now my list is cut in half again, so I go from 4 to 2. And then finally I find the match. Now this may seem like more work than it's worth, but the fact of the matter is, and we can look at this here, is that a binary search will find a value significantly faster. And I can give you some examples of what I mean by that. So here's your values through 20. So if we say, I'll say 12 again. It checks 10. Okay, now it's greater than 10, so this whole part of the list is taken care of, is gone. And it found a match after the second attempt. It discarded this top half of the list, and then it found its match. So in 3 attempts, it found a match in a list of 20. Now, if it were a sequential search, it would have taken on average of 10 attempts. The sequential is one after the other. So it would be, on average, half the size of the list. Now, for 20 rows, that doesn't seem like a lot. But if you look at a 1 million row list, that means sequentially, you'd have to look at, on average, at 500,000 rows. That's a lot. That's going to take a while. That's slow. But a binary search, believe it or not, will cut that list down and find a match in 1 million rows by only looking at about a dozen rows instead of 500,000. That's a significant difference. Significant difference in what you're talking about. And I have something where I can show you. Okay, so again, this shows you the list. If it's 0 to 12, the middle value is 6. So if your key is 11, and you look at 6, which is 50, the key is less than that. Now it cuts the list in half, because it realizes that the match can only be found in 0 to 5, looks at the middle value again. 11 is 7 is the middle. So it's greater than that. Again, it cuts the list in half. And it finds a match on 11 on the third try. Now again, with a small list, this doesn't seem like a lot. But the difference in time between a sequential search and a binary search increases exponentially as you go, as you increase the size of the list. So again, this shows you how it works. The key is 54. It's another example of how you cut the list down. Binary search method returns the index of the element in the list that matches the search key if it is contained in the list. Otherwise, it returns -1, just like the other one did. The insertion point is essentially the middle point, where you're going to look in the list. So here's an example of binary search, and I have that example here as well. Binary search. And we're going to give it the same list and look for a key, and then we can see how it goes through it and looks for the key. So, and we can output this as well. I can say system out.printf mid key is %. And it'll be mid. And this time, instead of doing a linear search, I'm going to do the binary search. Right, and we'll do this. Okay, so mid key is 7310. 11 is found at -2. Is 11 is there? Okay. Oh, actually, we didn't have a find. Sorry, I passed in 1 there. Let's try it again. So here, in essence, you can see it made 4 attempts to cut the list of, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 values, and it was able to find a no match in 4 attempts. On a sequential array, that would have been 8. It would have been on average 8. And we could put a whole bunch more in here if we want. And that's 18. Oh, okay. The problem with this list is it's not ordered. Alright. So the problem with this is not ordered. Now let's try something different. Give you an idea how this works. Int values, and I'm going to say 1000. We'll say, oops. New int. So let's just say values equals I. So it's going to put 1000 values in there, and it'll be sorted automatically. It'll be sorted automatically because it's going to be a numeric order. And we'll search for some really high number. I'm going to say 1000. Search for 888. High number. Let's see how many times it takes. Okay, so we found it. If we look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1000 rows, it took 10 attempts, right, to find it. We could do the same thing with the linear search. But we kind of know how many attempts it's going to take. Because it's linear, it means it's going to go in order. So it's going to take, in order to find it, it's going to take 888 attempts to find it. Let's just do this here. Let me set up a variable they can both use. Int attempts. And let's make this. For the linear search, it's pretty obvious what it's going to take. Now let's just leave that alone. We don't need it. Now if I go back to here, there's a couple of things we could do. Let's put some timing on it. How long will these take? So we'll do the linear search and we'll do the linear search as well. And this is a fairly large number. Okay, binary. We probably should pull the print statement out, actually. Okay, so the whole thing started at 15 seconds. The binary search took less than a second to find it, and so did the linear search. But we know the linear search went through 888 times. Okay, so that doesn't tell us much because we can't see the difference. Let's make it 10,000. And binary didn't find it. Oh, sorry. That needs to be that high too. Let's try again. Okay, they were both pretty fast. Again, but that's because we only looked for 888. Now let's say we're looking for 8800. And I think I will. In case of the binary search, we'll just say this here. Okay. Now the binary search said it found 888 in 13 attempts. Okay, that's pretty good. That's a 10. Remember, this is a 10,000 row array, and it took less than a second. Okay, the linear search also found it. Hold on for a second. The linear search will look for 888. Make sure it's apples and apples there. Still fast, although that's because the computer's really fast. But on average, it would have had actually the linear search would have had to have done 8,888 searches. There's no two ways about it. It's one after the other. Whereas the binary search did it in 13 attempts. Okay, let's make this thing even larger. And look for really large number. 17 attempts on the binary search. Compared to the linear search, still would have had to have done almost 90,000 searches. Still fast. And that's just because computers are really fast. Alright, let's see. It's 100,000, 100,000. Let's go for broke. Let's go for a million. Let's make it a really big number. Okay, 19 attempts on 1 million rows. Whereas the linear search would have done that many searches, essentially. It has no choice. It's got to go through every single one. Still fast, and that's just because computers are really fast, and we're going through integer values. I can tell you if you were looking for names or something like that, it wouldn't be nearly as fast. And we'll just go one more attempt, 10 million. And that's it, we'll move on. If it's just a... okay. 22 attempts on a 10 million row table. That's fast, considering that the sequential search is going to have to do an average of 5 million. Now, it's doing it really fast still, but we're only looking at numeric values. If we were looking at something more complex, I wish I could show milliseconds here. I wonder if I can show milliseconds. Hold on here. It's really what you need to see. Anyway, let's move on. But as you can see, when we get to some database stuff, we'll see why this is really important. And the only other way would be to, God, go for 100 million. Okay. Again, even on 100 million, is that right? Even on 100 million, it only took 22 attempts to find it. They all finished in less than a second. But that just goes to the speed of the thing. All right, let's move on. But you can see how it works. It essentially compares the values. If you've got a list, now the array method has something built in called a binary search. So smart arrays, which you have in Java, have a built-in binary search, so you don't have to write your own. Would it also work with characters and names? Yes, it would. That's important. It certainly would. It would have to, the name would, again, remember, characters are numbers. Characters are integers. There's no difference. And names it would too. It would do you'd have to sort them alphabetically. I mean, like right here, we have a list of characters. Right there, I have a list of characters. And it works exactly the same. There's really no difference. Okay, so the array has to be pre-sorted in order for that to work.